First, let me thank the organizers for the invitation, and it's a pleasure coming here. And KBS is my grand advisor, the advisor's advisor. So it's nice to be speaking in his conference. Okay, so I'll be speaking on multi-parameter E0 semi-groups. So this we were working with R. Srinivasan and his students for the past 3 years, and this is an outgrowth of those things. Okay, so traditionally an E0 semigroup is just a semigroup of endomorphisms on B of H, where the indexing set is a positive real line. So you have for every T positive, you have alpha T. Alpha T is an endomorphism of B of H, and it satisfies the semigroup law, that is alpha T is alpha S plus T, alpha S of 1 is 1, and of course it's a von Neumann algebra, so you would require that to be continuous in appropriate sense, and you also require continuity in T. But if you just look at the definition, there is no reason why one should restrict oneself to the positive real line. We can take any semigroup. You are just using the semigroup operation, so you can take any semigroup and start asking questions. So for us, for the purpose of this talk, I will assume that P is a closed convex cone in a Euclidean space. So it's convex, closed, and cone. Cone is just if you take a point and the whole ray is there. And for technical reasons, I assume that it is pointed, which is there is no line which is in the cone, and it spans. Spanning is not a big deal, because if it's not spanning the whole space RD, you can look at the space where it spans. Okay. So by an E0 semigroup, as I said, it's just for every point x in P, you have an unital normal endomorphism of BH, and it satisfies the semigroup law, and you have the condition that it should be continuous with respect to the appropriate topology, in the weak topology. And of course, we identify two E0 semigroups to be the same if one can be brought acting on two different Hilbert spaces if there is a unitary equivalence between them. Okay, classifying E0 semigroups up to unitary equivalence is a difficult problem. The basic equivalence relation in the subject is that of cocycle conjugacy. So you start with an E0 semigroup alpha x and perturb that by a unitary ux, then this, if beta x will also be an endomorphism, and for beta x to have the semigroup property, ux alpha x uy should be ux plus y. If this is the case, then beta x also will be an E0 semigroup, and we will not distinguish between alpha and beta. So we say that alpha and beta are cocycle conjugate if there is a cocycle which intertwines alpha x and beta x. So such an E0 semigroup is called a cocycle perturbation of alpha, and the subject of E0 semigroup is to study E0 semigroups up to cocycle conjugacy. Okay. So in fact, the theory was initiated by R.T. Powers and developed extensively by Arverson for the case of the real line, for the case of the positive real line. So we did something for the case of a cone. So first let me give a basic example of an E0 semigroup. So the first basic example is what is called the CCR construction using the symmetric Fock space. So let me just recall the basics of symmetric Fock space. So H is a Hilbert space and gamma H is the symmetric Fock space, and you have the exponential vectors. They are linearly independent and total, and you have this nice formula that the inner product of two exponentials is again an exponential of the inner product. So that's the thing, and there you have the Weyl relations, Weyl operators. So for a given unit, for a given point u in H, you have a unitary operator W on the symmetric Fock space, which translates the exponential vectors, that is E of V goes to E of U plus V. Of course, you need to put this factor so that it becomes a unitary. So this is called the algebra generated by W of U is called the CCR algebra, and the von Neumann algebra generated by that is actually it should be equal, because I am saying the von Neumann algebra. The von Neumann algebra generated by that is equal to the bounded operators on B of gamma H. So the Weyl operators generate the whole bounded operators on a symmetric Fock space. So the first example of an E0 semigroup is on the symmetric Fock space using this CCR construction. So here is the first example, that's the proposition. That is, if you have a continuous semigroup of unitary isometries on a Hilbert space, then each isometry will induce a endomorphism on the bounded operators on the symmetric Fock space, whose action on the Weyl operators is given by W of Vxu. So alpha x W of u is W of Vxu. So what do I mean by a strongly continuous semigroup of isometries? For every x you have an isometry, and it's a semigroup. So Vx Vy is Vx plus y, and it is strongly continuous. So you can prove that given a strongly continuous semigroup of isometries, there is a unique E0 semigroup on the bounded operators on the symmetric Fock space. The E0 semigroup is called the CCR flow associated to the isometric representation V. Just like you can construct, that is for the first, using the CIR construction, you have on one hand you have isometric representations, on the other hand you have E0 semigroups. So there is a natural construction, that is, if you start with an isometric representation, you can construct an E0 semigroup on the symmetric Fock space by this thing. This is called the CCR functor, and you can also do the same thing on the antisymmetric Fock space, and that is called the CAR functor. Okay, it's very natural to ask whether these two functors are the same or not. That is, whether the CCR alpha V is same as CAR alpha V, as if one is a cocycle perturbation of another. You can ask that, and in the one-dimensional case, it is true, and recently R. Srinivasan has proved that it is not true in the higher dimensional case. So this is one scenario that it's not just sake for generalization, it's you see some interesting things in the multidimensional world that you don't see in the one parameter world. No, the parameter P is R plus. The parameter P is R plus. So in the one parameter case, both the CCR and the CAR coincide, whereas recently R. Srinivasan has proved that in the multi-parameter case, the CCR and CAR need not have to be the same. So that's one difference that you see, that you see difference when you go to the higher dimension. When the parameter set is different, you see differences. Okay, I will illustrate a few differences in this talk. That's the purpose of this talk. And but before that, I need to give an invariant for. This is the notion of product systems due to Arveson. The basic theory stays intact. That is, the Iverson's theory of E0 semigroups and product systems, whether you are in the one-dimensional case or in the multi-dimensional case, stays intact. And that is a nice thing about it. Yet there are differences. So I think it's a nice thing to investigate in this direction. So what is a product system? So alpha is an E0 semigroup. You look at for every x in P, Ex, which is all those operators T. So you think of alpha x as a representation of bounded operators B of H on B of H. And T is those which intertwines alpha and the identity representation. Alpha x is a representation. You look at all those operators which intertwines the representation alpha and the identity representation, which is A. So that is the space of intertwiners for alpha x, and it's a separable Hilbert space. Okay, I need to tell what the inner product is. If you take two elements S and T from this intertwining space, S intertwines alpha and identity, T intertwines alpha and identity. So T star will intertwine identity and identity. So if you compose T star S will intertwine identity and identity. That means it commutes with all operators. So it has to be a scalar, and you call that scalar as inner product ST. With respect to this inner product, this becomes a separable Hilbert space. In fact, you can recover the endomorphism alpha x from this intertwining space. It has a product structure that is, if you take an element S from Ex and T from Ey and compose St, that will be in Ex plus Y. So you have a product from Ex to Ey to Ex plus Y, and that would also be a unitary. Not only it's just well defined, it's a unitary between these Hilbert spaces and this Hilbert space. So this Hilbert space is in fact the tensor of Ex tensor Ey. So given any E0 semigroup, you have this bundle of Hilbert spaces. For every x, you have the intertwining space Ex, and you have this bundle of Hilbert spaces. And this bundle is not just a bundle, it has more structure, it has a product structure. So it's a field of Hilbert spaces which has a product structure. That is called the product system associated with alpha. So let me write. Yeah. So if you have an alpha, I have a bundle of Hilbert spaces, disjoint union x in P, Ex, and for every x, Ex is a Hilbert space, and there is a multiplication from Ex is a Hilbert space. I'm writing the same thing, sorry, it's and there is a multiplication from Ex cross Ey to Ex plus Y, S comma T goes to S dot T. So this multiplication will descend to the tensor product, and this bilinear map descends to the tensor product and gives a unitary between this Hilbert space and that Hilbert space. So any bundle of Hilbert spaces having this structure, having these two structure, of course I'm hiding the technical details under the carpet, but anything which has this any field of Hilbert spaces having this product structure is called a product system. And given any E0 semigroup, you have a product system. And the famous theorem due to Iverson is that given any E0 semigroup, you have a product system. and two E0 semigroups are isomorphic if and only if the product systems are isomorphic. Moreover, any field of Hilbert spaces which has this product structure has to come from an E0 semigroup. So that is Iverson's theorem, and this for the case of one parameter, that is when P is 0, infinity. In the one parameter case, there is Iverson's theorem, and the verification of Iverson's theorem in the higher dimensional case was taken up in Murugan's thesis, a student of R. Srinivasan. So the main result is the following. So two E0 semigroups alpha and beta are isomorphic, that's cocycle conjugate, if and only if their associated product systems are isomorphic. And two, this is the first one is just, it's not at all a theorem, it's just step by step argument of Iverson. The second one is again an imitation of Iverson's argument, but this requires some non-trivial work. So any abstract product system, that is any field of Hilbert spaces which has this product structure, is isomorphic to a product system of an unique E0 semigroup. So whether you want to study E0 semigroups or product systems are one and the same. Okay? So now let me tell the few differences between the one parameter theory and the multi-parameter theory. In the one parameter world, so I will explain these terms. In the one parameter world, you know that decomposable product systems necessarily have a unit. Whereas in the multi-parameter case, decomposable product systems need not have to be a unit, need not have to have a unit. In the second, if you take the opposite of a product system, that is, the opposite of a product system is very easy. It's the same thing. The product rule is just flip. ST is, you define a new product rule. You define a new product rule. Suppose you have a product system. It's a field of Hilbert spaces having a product structure. You can define the opposite. You keep the Hilbert spaces as such, but change the product. Of course, this product should be an associative product. You change the product, you define S dot T to be TS. Because T is in EY, S is in EX, TS will again be in EX plus Y. So this is the opposite of the product system. In the one parameter case, if you take the CCR flow, the opposite will again be a CCR flow, and it will be the same CCR flow. The CCR flow is the one that I said that from an isometric representation you can construct two E0 semigroups. One is through the CCR construction, another is through the CAR construction. In the one parameter case, the opposite of a CCR flow will again be a CCR flow, and it will be the same CCR flow. But in the multi-parameter case, the opposite of a CCR flow will be a CCR flow, but it may not be the same one. So these are two differences. So I have explained this opposite, and the first one I told in the beginning itself. This was due to Srinivasan, that the car flows and CCR flows need not be the same. Whereas in the one parameter theory, all these things are not true. That means decomposable product systems have a unit. The opposite of a CCR flow is the same as the one, and the car and CCR coincide. So because of these things, it looks interesting. So let me explain. So let me explain what I mean by the first statement in the remainder of this talk. So what is a decomposable product system? So you have an E0 semigroup, and you have a cone, and the cone induces an ordering on RD. It's a partial order, x less than or equals y if y minus x in P. If P were your 0, infinity, this is your usual ordering on the real line. So this is a partial order. Okay, so you need a few definitions. So alpha is an E0 semigroup and E is its product system. There is no difference between E0 semigroups and product systems. So you take a point x in P, a vector u in x, Ex is called decomposable if given any point y less than or equals x. You can write Ex as where is the duster? You can write Ex as Ey tensor Ex minus y because it's, and if it is a decomposable vector of that tensor product, you call that vector as decomposable. So a vector u is called decomposable. There is one more thing, that is it should be a non-zero vector. It's called decomposable if it is non-zero, which I forgot to write it here. If it is non-zero and given anything less than x, you can write u as vw. Anything you can always split, it is always decomposable. So that's why it's called decomposable. We denote the set of decomposable vectors by dx. The product system is said to be decomposable if you take the product of two decomposable vectors, it's again decomposable, and the set of decomposable vectors is a total set in Ex. That is, the span closure is the whole Ex. The first condition is not there in the one parameter case. In the one parameter case, this will follow from the definition because the ordering that you have is a total order. So using that you don't need this condition at all in the one parameter case. But in the multi-parameter case, you need this condition. It's not true in general that if you take product of two decomposable vectors, it is again decomposable. So you need this as a part of a definition. So this is, the product system is said to be decomposable if this is the thing. And Arvesen's groundbreaking work is the following, that is, if P is 0 infinity, that is the one parameter case, I should have read, suppose P is 0 infinity, then Arvesen's result says that the map V going to alpha V, that is the CCR thing, that is from an isometric representation using the CCR construction, you can construct an E0 semigroup, is a bijection between the set of pure isometric representations, that is any one parameter isometric representation is essentially a shift and a unitary. Any isometry is just a shift and a unitary. Just like that, a one parameter isometric representation is the shift on the positive real line plus a unitary part. You call that isometric representation pure if there is no unitary part. It's only a pure shift. This sets up a bijection between the isometric representations and decomposable E0 semigroups. So you know how decomposable E0 semigroups are in the one parameter setting. It is just alpha V. It's just the CCR flows. So in the one parameter case, so one of the characteristics of the CCR flow is that a lot of units. So what is a unit? A unit is so it has, this is the product system. This is over P. This is a Hilbert. This is a bundle of Hilbert spaces over P. Unit is, it's a cross section of E, which is multiplicative. So that is, for Ux is in Ex, Ux Uy is Ux plus y. Yeah, and Ux should be non-zero. So it's a nowhere vanishing cross section of the product system which is multiplicative. So in Arverson's proof that the map sorry, V going to alpha V is injective, in the Arverson's original proof that the notion of units form a big role. He computes the units of alpha V explicitly, and using the units he assigns a number called the index, and he proves that the index is a complete invariant for a CCR flow. So that is the injectivity part. The surjectivity part is, I'll explain. So in the one parameter case, a decomposable product systems have units in abundance, but this is no longer true in the multi-parameter context. What we do have in the multi-parameter case is that yes, the functor is injective, that is, if alpha V and alpha W are isomorphic, then V and W are unitarily equivalent. If you have a decomposable E0 semigroup and which have a unit, then it must be a CCR flow. So in Arverson's theorem, in the one parameter case, decomposability itself implies has a unit. Whereas here, if it is decomposable and has a unit, then it is a CCR flow. So, and there are indeed uncountably many examples of decomposable E0 semigroups which do not have a unit. Okay, so let me tell how this too is proved. It's really an imitation of Arverson. So, but it's so the basic steps of proving both 1 and 2 is that so from a decomposable product system, when P is 0 infinity, Arverson constructs an isometric representation. Okay, Arverson constructs an isometric representation, and then he solves a lot of cohomological problems. V, to show that the things that you started with, you start with an alpha, you construct V, then you solve this cohomological problem to conclude that alpha is same as alpha V. So if you want to adapt the proof of Arverson in the multi-parameter context, the first step is to construct this isometric representation, and the crucial thing in Arverson's proof is that it's again the total order of the real numbers, the ordering in the real numbers is totally ordered. That is, any two elements are comparable. So that is crucially used here, and one of the main non-trivial part is to overcome that in our case, which is what was done, and then all these cohomological problems you have to solve, and these cohomological problems arise precisely because we don't know whether a decomposable product system has a unit to start with or not. So if it has a unit, then this step does not occur, this step does not arise at all, and simply this step is required to conclude that alpha is isomorphic to alpha V. And of course there are cohomological abstractions, and it would be nice to understand exactly what these cohomological abstractions are. The examples that illustrate that there are cohomological abstractions is what I mean by 3, that there are indeed uncountably many examples of decomposable E0 semigroups which do not have a unit. So it would be nice to understand exactly what these cohomological abstractions are. Okay, so let me end my talk with.
So when you say the third one, you're saying uncountably many which are
Of course, yeah.
That you know by some other because the product systems are not the same. How do you know that?
No, that is that's I'm going to give. Yeah. So instead of giving the E0 semigroup, I'm going to give the product system. So I'm assuming that the dimension is bigger than 2, because if the dimension is 1, there is nothing, it's already known. So look at the dual cone. I'm looking at the interior of the dual cone, that is all those vectors which make a positive angle with, which makes an acute angle with everything in the cone, and take 2 points lambda and mu from the interior. You take the one parameter shift semigroup on L2 0 infinity and use that one parameter shift semigroup to construct an isometric representation of P using this formula. So A going to mu A is a semigroup homomorphism. So you compose with the shift, you get a semigroup homomorphism from P to the isometries. So you get a semigroup of isometries. So that's an isometric representation. You consider your usual CCR flow and let E be the product system. I'm going to define a new product on E. So I'm defining E bar, which is E. I'm defining a new product like this. So take S in E bar of X, T in E bar of Y. Define S dot T is, you introduce this Weil factor. The Weil factor introduced is such that, so that the this part, that is after S, after S, what is there is again in EY. So this rule is well defined, and one can indeed check that this defines a associative product on the bundle of Hilbert spaces. So we know that this is a product system, and you know that there is an E0 semigroup, because every product system there is an associated E0 semigroup. So this is a product system. So let me call this product system as E bar lambda mu, just to stress the dependence of lambda and mu. So the following are equivalent. The product system E bar lambda mu has a unit. It will have a unit if and only if lambda and mu are scalar multiples of each other. So because you are in the higher dimensional case, the interior mu star would also be a cone, and it will be the same dimension. You can always choose two elements which are not scalar multiples of each other. So you can choose such a thing, and then the product system will no longer have a unit. And there are uncountably many, because E bar lambda mu 1 and E bar lambda mu 2 are isomorphic if and only if mu 1 and mu 2 are scalar multiples of each other. So if you combine these two things, you get uncountably many examples of decomposable E0 semigroups which do not admit a unit. But these are examples, and it would be nice to understand what exactly is going on with the cohomology. What is the correct cohomology, and is it possible to compute it, and so on and so forth. Okay. Thanks a lot for the attention. Thank you.
You said that the usual parts of the theory of one parameter semigroup go through for this multivariable case also.
Yeah.
So
by which I meant only. Okay. Carry on with the question.
So natural question is, what about, is there an analog of this Carter's theorem about infinitesimal generator and things like that?
Well, as far as I know, that in the one parameter theory, the isomorphism, the thing between product systems and E0 semigroups go through. That's what I meant by saying that the basic theory goes through. After that, the other things need to be explored. It's not clear.
When there are units.
Yeah.
When there are units, so can you parameterize the units?
For
the product system.
Because if there are units, you can, yeah, because it will be isomorphic to the CCR flow, and the CCR flow would be the one coming from this isometric representation VA. You can compute the so for this example you can indeed parameterize. Yeah.
Any more questions?
Is it the case that all of your problems arise as soon as you go from dimension 1 to dimension 2 or more? Or does anything work in dimension 2 nicely?
Just for, I mean, yeah, there is a difference between dimension 1 and dimension 2, dimension greater than or equals to.
In this case, but I mean, Srinivasan's example, is that in what dimension does he have to work in?
It happens for anything beyond 2,
From 2 upwards?
2 upwards, yeah.
Any more questions?